The Higgs boson is an elementary particle in physics. In the standard model of physics, it is a reason that most particles have mass. It was predicted theoretically in the 1970s before experimental verification that came in 2012. The proof of its existence gave further strength to the standard model of physics. A concept called gauge invariance had great success when applied to the strong force and electromagnetic force. This was because it predicted that the mediating particles for the weak force, the W and Z bosons, should be massless. In reality, experiments showed that the W and Z bosons had mass. Now, physicists either had to discard the gauge theory approach to the weak force or find a separate explanation for why the W and Z bosons had mass. In a set of papers written in the early 1960s, Peter Higgs, Robert Brout, Francois Engelbert, and other physicists suggested how the W and Z bosons could have mass without violating the principle of gauge invariance. They suggested that a field is present throughout the universe. This field interacts with the W and Z bosons, giving rise to mass. They developed the ideas of Yoricho Nambu, who suggested in 1960 the idea of spontaneous symmetry breaking, a crucial lead in the matter. A general feature of modern particle physics is that every field has an associated mediator particle. In the case of the Higgs field, the associated particle was the Higgs boson, the so-called God particle. This theoretical prediction happened at the same time the Higgs field was predicted in the 1960s. However, the actual detection of the Higgs boson took much longer. The way physicists went about finding the Higgs boson was using equipment called particle accelerators. They are immensely long tubes in which particles are taken to high velocities and are made to collide. In the process, the particles form and decay, giving off a series of other particles as predicted by theory. Physicists knew the properties and decay process of the Higgs boson from theory, so all they had to look out was for any sign of these particles. This was easier said than done for several reasons. The energy required in the collisions to produce the Higgs boson was very high. The technology required to get there also took several decades, all the way into the 2000s and the 2010s. Further, most decay products of the Higgs boson are commonplace and turn up in other particle collisions. Separating the real Higgs boson decay products from the rest was not easy. Only a few decay products were distinctive, but these were also produced very rarely. The Higgs boson was discovered in June 2012 by two teams working in the Large Hadron Collider, the world's largest particle collider. The particle was first identified as consistent with the Higgs boson. Its properties such as its mass and spin gave strong indications of the fact. Further, in July, a third independent set of evidence gave further confirmation of the fact. The Higgs boson was the last proposition of the standard model that needed verification. Its discovery settled this issue. It also opened up new areas for research in physics, possibly leading to new physics that is beyond the standard model. There is much to be known about this particle too, such the mystery about its own mass, which is not predicted in theory but must be calculated. It is expected that in answering these questions, particle physics will go a long way ahead and will help us gain a deeper understanding of the universe.